Okay, now we're going to look at number 80 in Chapter 10 of Serway and Jewett, which is based on one of my favorite physics demos of all time. You see, we've got a board, or really a meter stick. The ball all the way at one end of the meter stick, a distance L from the pivot, the hinge. We've got a cup most of the way down the meter stick. It's a distance we'll call RC, the radius of the cup from the pivot. And what happens is when you let go, the board falls away faster than the ball, and the cup gets to a point directly below the ball a little bit in enough time that the ball lands in the cup. The angle theta is the angle that the board initially makes with the table. So we can see if we draw just the relevant right triangle, theta is here, the hypotenuse is the entire distance L, and the adjacent to that to the angle is RC, the radius of the cup. So the idea, the problem asks us to show that the board falls away faster than the ball when the angle is less than 35.3 degrees. So that's our task. Okay, so we need to categorize the problem. We've got two objects to model. We've got the ball and the board with the cup attached. The ball's easy. That's just a particle in free fall, right? It's falling with acceleration g. So we want to show that when the angle is less than 35.3 degrees, the ball accelerates, or the board accelerates more than that. The board with the cup attached, that's not a particle in free fall, but we can model it as a rigid body under a net torque, right? Because it's rotating around the pivot, the end that's in contact with the table. Since it's a particle or a rigid body under a net torque, we'll need to analyze it using the fact that the sum of the torques is going to be moment of the rotational inertia times angular acceleration. Right? That'll be the main way we find the acceleration of the cup. Right? And since the cup is just a point on the board, we're pretty sure we're going to have to use the ever useful fact that for any point on the board, the angular acceleration of the object is equal to the acceleration of that point divided by the distance of that point from the pivot. Right? So we have alpha equals the acceleration of the cup over RC. So the idea now is that we want to show that the critical angle for the board to fall away is 35.3 degrees. Right? We know that if the acceleration of the cup is larger than g, the acceleration of the ball, the board falls away, right? And the trick works. Right? If the acceleration of the cup is less than the acceleration of the ball, which is g, the board does not fall away from the ball, right? The ball just kind of slides down the board as it falls. Right at AC equals G, that's the critical angle, right? And that's what we want to show is 35.3 degrees. Okay, well we know we're gonna look at sum of torques equals I alpha, and that's how we're gonna do this. So let's go ahead and draw a free body diagram of the board. So here's the board. We know we've got gravity acting on it at its center of mass, a point halfway along the board, right? And we've got also a normal force acting right at the pivot from the table. We know that won't produce any torque because it's acting right at the pivot. And of course, you know that each torque can be calculated from, or the magnitude of each torque can be calculated from its distance from the pivot times the strength of the force times the sine of the angle between those two. All right. So the sum of the torques then is just 0 from the normal force, and then from the force of gravity, the distance of that force from the end, from the pivot, is just L over 2. The strength of that force is mg. And then we have the sine of the angle between the two. We've got to be careful, though, because the angle between R and F is this angle here, right? Which isn't theta as labeled here. It's actually the angle I'm labeling phi up here. So really, this should be sine phi, not sine theta, right? Because phi there We can't use theta for every angle, right? Phi is the angle between R and F. That's a tricky point there. And we're going to have to use the fact later, so I'll point it out now. You're going to have to use the trig fact that the sine of that angle phi is going to be equal to the cosine of our real angle theta, and you'll see why that's needed in a second. Let's see. So now that's the sum of our torque. So that's the only force providing a torque, L over 2 mg sine phi. That's going to equal I. You can easily look up or fairly quickly calculate the rotational of inertia of a rod around an axis at one end is 1/3 mr squared, where of course the length of our rod is here lowercase l. That's the moment of inertia. And then the angular acceleration, we said earlier, we know the angular acceleration is just the acceleration of the cup over its distance from the end, so AC over RC. So that's bulk of the analysis there, right? We've applied Newton's second law for rotation to this problem. We've got a few unknowns, and now we can try to will the number of unknown variables in this equation down. Let's replace things with things that we know. So let's see, L over 2 mg. We don't want to leave phi in our equation here because our givens are in terms of the angle theta between the table and the board. So we can replace sine of phi with cosine of theta. Right? A second ago we said that was true. That's just a trig identity. Those are complementary angles. Equals 1/3 ml squared. Now, we're looking for the critical angle, right? Where if the angle is low enough, the torque provided by gravity is big enough to make the board fall away, right? So right at that critical angle, AC, the acceleration of the cup, has to be equal to G. So I'm going to replace AC with G in my equation here because I'm looking for the critical angle. And RC, well, maybe I can write that in terms of L. If I look back at the relevant right triangle for the problem from SOHCAHTOA, I can see that the cosine of the angle is equal to the hypotenuse, or sorry, the adjacent, which is RC over L, right? So that just means that RC is L cosine theta. So I'll plug that into my equation down here, L cosine theta. Now I have a lot fewer different variables, and let's see what I can cancel out. Right, I've got an L down here that can cancel out with one of the L's up here. I can cancel out an L on each side of the equation to get rid of the rest of the other L's. M's cancel. G's cancel. So now I can rearrange this, and I get, if I multiply both sides by cosine theta, I get cosine squared of theta, and then I multiply each side by 2, will be 2/3. So the critical angle, that gives us that the critical angle would be the inverse cosine of square root of 2/3. Then, of course, if you plug that in, check that on a calculator, you will see the inverse cosine of 2/3 is indeed 35.3 degrees, just as we had been looking for. See, easy. For part B, right, part B asks you to show that the cup is 18.4 centimeters from the moving end. Well, that should be easy to do because you already have an expression for RC in terms of known quantities now. Thanks for listening.